All right, so in this video, I'm going to be going over pages 11 and 12 in the notes packet. So here's where we're starting to simplify radicals. So what you mean by simplify radicals is you might remember simplifying fractions, right? So 8/6 is equal to 4/8 is equal to 1/2. Well, you can actually do the same thing with radicals, right? Where you turn it from something kind of with a bigger radicand into something with a smaller radicand, right? You want to simplify the radicand as much as possible, make the radicand as small as possible. So square root of 32 becomes 4 root 2. Cube root of 135 becomes 3 times the 5th root of 5. Sorry, that should be a cube root there. 3 times the cube root of 5. And let's, we're going to explore 2 ways that we can make this happen. So the first one is going to be a shortcut method. It's going to be faster, but only useful for some problems. And then there's a long way you can use for any problem. So we're going to explore both of them, but you are welcome to use whichever is more comfortable for you on any given problem. So starting with the shortcut method, we're going to exploit this property. Remember, we learned that the square root of a times b is equal to the square root of a times the square root of b. And to do this, we're going to want to be very familiar with our perfect squares. So I'll fill those in real quick. Remember, 1 squared is 2, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144. All right. So the trick here is if we can use this property, if we can rewrite the radicand as 2 different radicals, one of them being a perfect square, then we can simplify the perfect square and leave the other number as is. So for example, with the square root of 300, there's nothing stopping us from writing that the square root of 100 times the square root of 3. Now the square root of 100, that's easy to simplify, that's 10, so it becomes 10 root 3. Square root of 80 might be a little bit more difficult at first glance, but that's actually the square root of 16 times the square root of 5, and the square root of 16 becomes 4, so that becomes 4 root 5. Same with 108, we can actually do the square root of 36 times the square root of 3, and then that becomes 6 root 3. So this method can be very efficient if you can find a number that it works for. So we can also do the same thing with bigger indexes, but again, it's trickier. So like the cube root of 24, you can rewrite that the cube root of 8 times the cube root of 2, or the cube root of 3, sorry. Cube root of 8 is 2, so this is going to become 2 times the cube root of 3. Looking at this one, the cube root of 54, you can rewrite that as the cube root of 27 times the cube root of 2, which boils down to 3 times the cube root of 2. All right. Looking at the 4th root of 96, well, that can become the 4th root of 16 times the 4th root of 6, and the 4th root of 16 is 2, so that can become 2 times the 4th root of 6. All right, so what if we're looking at it and it doesn't immediately jump to us how we could find a perfect square, perfect cube, perfect fourth, whatever, right? What if the shortcut method breaks down? Well, in that case, we're going to use the tried and true version. We're going to use prime factorization. So with prime factorization, we're going to break down the number as far as possible. So if we look at 80, well, what are 2 numbers that multiply to 80? What if we said 4 or 40 and 2? What are 2 numbers that multiply to 40? Well, 8 and 5. What are 2 numbers that multiply to 8? 2 and 4. What are 2 numbers that multiply to 2? 2 and 2. Notice how all of these numbers left are prime numbers, meaning that they can't be multiplied together, or they can't be, there's nothing that multiplies evenly into them besides themselves in 1. So let's try this with a bigger number. So for 1400, we can do 20 and 70. We can do 2 and 10, and 7 and 10. We can do 2 and 5, and 2 and 5. Notice how these are all the prime factors there. All right, so how are we going to exploit this to actually simplify radicals? Well, the answer is we're going to make use of this property. So remember that the square root of a times the square root of a, that just becomes a, right? Think about that as a to the 1/2 times a to the 1/2. Well, if we add those powers, we're going to get a to the first, which is just a. Same with if we have b, the cube root of b times the cube root of b times the cube root of b. Well, that's the same as just b, right? We can also think about that as the cube root of b cubed, and those are going to cancel each other. Same thing if we have 4 fourth roots, well, that's just c. So when we get to our prime factors, if we have a full set of any of our prime factors, then we can simplify that out. So let's see what that looks like. So for the square root of 1400, we can do the square root of 2 times 2 times 2 times 5 times 5 times 7. Right, those come straight from our prime factors up here. Once we have that, we're looking for our index here is 2, right, because it's a square root. So it's not written, but it's an implied 2. So we want to look for any sets of 2. So I'm seeing here, so I have 2 2s there, and I have 2 5s there. And what I'm going to do is I'm going to write those outside the radical. And that's because if we were to break this up, we could do the square root of 2 times 2 times the square root of the rest of them. And we know that the square root of 2 times 2 is the square root of 4, which is just 2. So whenever we have a full set, we can transform it. We can take it out of the radical. We can make it a whole number, right? Because the square root of 2 squared, 2 times 2, is just 2 on the outside. And now, to finalize our answer, we're just going to recombine everything inside and outside the radical. So outside the radical, we have 2 times 5, that's 10. Inside the radical, we have 2 times 7, that's 14. All right. And so if we want to do this from the start, we're going to start with our prime factorization, then write it all in a radical and pull out any full sets. So what are factors of 1,125? Well, I know that it's 25 times 45. And then each of these can be broken up. That's 5 and 5. That's 9 and 5, which then can be 3 and 3, meaning that we can write this the cube root of 3 times 3 times 3. Oh, sorry, just 3 times 3 times 5 times 5 times 5. Now you can see that we have a full set of 3 5s, so we can bring them outside. You can get 5 times the cube root of 3. And that's our answer. That's as simplified as it gets. So we can do the same thing down here. 20, that's 4 and 5, that's 2 and 2. Square root 2 times 2 times 5 is 4 root 5. 150, if we did 15 and 10, get 3 and 5, 2 and 5. And now we have a number out in front. But remember, if we just simplify the radical, we then need to multiply our whatever number we pull out of the radical with that coefficient. So what that would look like is this would then be 5 times the square root of 2 times 3 times 5 times 5. We have 2 5s, so we can pull them outside. We want to multiply that with the 5 that is already outside. That's going to become 25 square roots of 6. All right. Looking at 108, so we can do 54 and 2. We can do 27 and 2. We can do 9 and 3. We can do 3 and 3. It's going to be the cube root of 2 times 2 times 3 times 3 times 3. See, we have a set of full 3s to bring outside. We can do 3 times the cube root, and then what's left inside, 2 and 2, that's 4. Then we can do the same thing over here. 128 and 10, which becomes 2 and 5, 64 and 2, 8 and 8, 2 and 4, 2 and 4, 2 and 2, 2 and 2. Means this is going to be the fourth root. 2 times 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 5. So, just in case, we have 1, 2, 3, 4, 5, 6, 7, 8 2s, and 1 5. So now we have 2 full sets of 2. You can pull those out front. So we're going to have 2 times the fourth root of 5, which means our final answer is 4 times the fourth root of 5.